Welcome back to our channel Sankalp Study Success. Today we are going to see about the next topic, which is Euclidean algorithm for finding the GCD. This is the most important algorithm which we have, and you can expect many questions from this algorithm. We will come into this. First of all, what is Euclidean algorithm? It is the most efficient method to find the GCD of two numbers, which is based on quotient and the remainder technique. Based on the quotient and the remainder technique, in the efficient way, you can find the GCD of two numbers. For example, we have already seen what is a remainder theorem is. That is, A is equals to BQ plus R, where A is greater than B, correct? A is equal to BQ plus R is the remainder theorem. Using this theorem, you can easily find the GCD of two numbers by using Euclidean algorithm. Now, let us see this theorem, which is the most important theorem, and you may get it for 5 to 7 marks in the question. So, A is equals to BQ plus R, then GCD of A comma B will be is equal to GCD of B comma R. Now we will prove this theorem. Now always, when you will prove a theorem, always consider the given data. Consider the given data. A is equals to BQ plus R, and now consider this as D1 and consider this as D2. See here, we are considering the LHS as D1 and RHS as D2. The one is the equation 1 and the other is the equation 2. First we'll go with only LHS, then we will proceed with the RHS. Here D1 is equals to GCD of A comma B. That means what? D1 is a common divisor of both A and B, correct? It will divide both A and B. So here it says that D1 divides both A and B. Now A is equals to BQ plus R. You can also write it as R is equals to A minus BQ. If D1 is dividing both A and B, then it will also divide R and B, correct? So, if D1 is the factor of A and B, D1 will also be the factor of B and R. That's the reason here we are saying that any common divisor of A and B will also be the common divisor of B and R. Now this is completely about LHS. Now we will move to the RHS part. That is, D2 is equal to GCD of B comma R. That means what? A is equals to BQ plus R. If D2 is the GCD of B comma R, that means D2 is the common divisor of both B and R, correct? So, if D2 is dividing B and R, then D2 will also divide A comma B. That means what? Any divisor of B and R will become divisor of A and B. That means you can see that this statement and this statement are quite one and the same. That means what? LHS is becoming equal to RHS. So what can we see from this? GCD of A comma B will be equals to GCD of B comma R. When is this possible? When A is equals to BQ plus R. This is correct. When A is equal to BQ plus R, then GCD of A comma B will be equal to GCD of B comma R. So in this way you need to prove the theorem so that you can get easily 5 to 7 marks in your external exams. Now moving to the next theorem. For this theorem, let us take one example. I'll explain you with an example so that you can understand the theorem more clear. Let's take an example. We'll take two numbers 24, 32. By applying remainder theorem, So by applying reminder theorem, which will be A and which will be B? We are saying that A is greater than B. That means what? A is equals to 32 and B will become 24. Correct? Now, when you apply A comma B in this equation, 32 will become 24 into 1 plus 8. Correct? Now, again continuing till you get the remainder as 0. 24 is equals to 8 into 3 plus 0. 3 8 are 24, so we'll get the remainder as 0. Now we got the remainder as 0. So we can say that this is the GCD of 24 comma 32. So GCD of 24 comma 32 will become 8. By following the same procedure, we can prove the second theorem very easily. So let us see here. He is considering two integers a comma b. A comma b are two integers here, such that r1 is the remainder when a is divided by b. That means, how do you write? A is equals to b cube plus r1. When a is divided by b, we are getting the remainder as r1. Okay, clear? Now r2 is the remainder when b is divided by r1. That means what? R2 will be the remainder. When it will be the remainder? When b is divided by r1. Is it true? Yeah. Now the third statement, r3 is the remainder when r1 is divided by r2, and so on. So it goes on like this. After that, if rn plus 1 is equals to 0, that means whenever you go on like this till the remainder becomes 0, then the last non-zero remainder rn is the GCD of a comma b. That means what? Till the remainder becomes 0, you have proceeded with the same procedure, and the non-zero remainder, that is 8, that is the non-zero remainder, which is the previous one. This will be the GCD. So let's prove the theorem. Here we have considered a comma b as the two integers a comma b, where a is greater than b and b is greater than 0. That means both the numbers are greater than 0 and a should be greater than b always. Now, by using these statements exactly, we have written that a is equals to bq1 plus r1. Where a is dividing b, then we are getting the remainder as r1. Then again, b, when it is divided by r1, sorry, q2 here, we'll get the remainder as r2. You can see here. In the same manner, when r1 is divided by r2, then you will get the remainder as r3, and the process moves on. So by combining all these equations, b is equals to r1 q2 plus r2, and so on like this. What is the last remainder? Rn plus 1. When this becomes 0, then Rn is the GCD. So GCD of a comma b is equals to GCD of b r1, which is also equal to the GCD of r1 r2, and so on when you go till rn minus 1 comma rn. When rn commas 0, that means what? If any one of the number is 0, then the number itself is the GCD. We have already seen in the previous lecture. So Rn is the GCD of the given two integers. You can also, for the better understanding, you can also take one more example. Let us take the numbers as 18, 6, which is the most easiest one, I think. You can write it as 18 is equals to 6 3s are 18, right? If it is only one step, then directly 6 is the GCD. Okay? If the remainder is 0, the non-zero remainder 6 will be the GCD of the given two numbers. Okay? This is also the most important one. The first two theorems are the most important theorems. This is the first one, and this is the second one, which is the most important theorems which you can expect in the external exams. And coming to the last theorem which we have in our syllabus is the theorem 3, that is which we have already discussed in the previous lecture, which is the linear combination, expressing two numbers in a linear combination. That is nothing but GCD of a comma b is equals to UA plus VB, where U and V are integers. Expressing in a linear combination of AB is the theorem. Now, how do we need to prove this theorem? How can you express two numbers in the form of a linear combination? Let us see. Here we are discussing about the Euclidean algorithm. So we will apply Euclidean algorithm to A and B. That is, you can see here, right? Rn minus 2 is equals to Rn minus 1 Qn plus Rn. This is what, from the remainder theorem, we can write it like this, where Rn is less than Rn minus 1, correct? Now, can we change? Let us see here. We'll write it here. Rn minus 2 is equal to Rn minus 1 Qn plus Rn. Now, can you write Rn from here? Rn is equals to Rn minus 2 minus Qn Rn minus 1. Now, can we write this as Rn minus 2 plus of minus Qn into Rn minus 1. That means what? Plus into minus will again get the same thing, right? So, Rn is equals to Rn minus 2 plus minus of Qn Rn minus 1. Now, similarly, Rn minus 2 we have written in this form. Similarly, Rn minus 1 can also be written as Rn minus 3 plus minus Q plus of minus Qn minus 1 Rn minus 2 in the same manner. So, let us see here. Now we need to simplify the above given expression. Rn minus 3 is here, correct? Rn minus 3, it is written in the same way, of minus Qn, okay, plus there is one Rn minus 2 here and also one more term with Rn minus 2. We are writing it in this manner. Now, Rn minus 3 of minus Qn is as it is, right, as it is, and Rn minus 2, if you take common, you will get 1 plus Qn minus 1 into Qn. That means what? A number into an integer plus a number into an integer. That means UA plus VB. You will get it in this form. Previously, we have seen it as alpha A plus beta B is equals to GCD of A comma B, correct? In the place of alpha and beta, now we are considering as U and V. You can consider alpha and beta, U and V, L and M. It is up to you. You can consider anything. So we have proved it that we can express any two numbers in the form of linear combination. Okay. Now, let us see with an example so that you can understand more better. You can understand it very clearly. And the first example here is, we'll go with the first example, which is here, GCD of these two numbers. These two numbers are very big numbers. Till now we were doing with only small integers, correct? Now we'll do it with the big ones, 42823 and 6409. Now, when you do it with this, A should be greater than B, correct? So we will consider this as A and we will consider this as B. So how do we write? 42823 is equal to 6409 into 6 times less 4369. You can do it, correct? Now we will consider this again. Why do we considering it as, why shall we considering again? Because till the remainder gets 0, you need to continue the same process. Okay, 6409 is equals to 1 into 4369 plus the remainder is 2040. Now again we need to continue because the remainder is not yet 0. 4369 is equals to 2 into 2040. We are getting the remainder as 289. Again we need to consider. 7 into 289 will give the remainder as 17. See here, we are having the continuation also, so that you can see and practice it. 17 into 17 times is 289, correct? Yeah. So we got the remainder as 0. So non-zero remainder, which is 17, is the GCD. So GCD of 42823 and 6409 is equal to 17. Do we get the same answer? Yeah. So we have found the GCD of two numbers using the Euclidean algorithm. Okay, this is the most important algorithm. I'm stressing it because you may get it for the external exam. Now you can also practice one more example, 4076 and 1024. You can find the Euclidean algorithm in the same format which we have done in the first example. Okay, this is the same problem so that you can practice. Now let's see the last question in this lecture, which is the third one. This is of different models, so I'm going to explain it for you. Find the GCD of 615 and 1080 and find the integers u and v such that GCD of these numbers should be equal to 165u plus 1080v. What can we understand from this? It is a linear, expressing the GCD in the form of linear combination, correct? So we need to find, first we need to find the GCD of these two numbers, then we need to express it in the format of linear combination. That means you need to find u and v. How do we do this? You know, first what do we need to do? First step is to find GCD. This can be done by you because we have already done it. The second step is linear combination. Now let us see the second step. You need to find out this GCD by using Euclidean algorithm. See here, I'll explain it. You can practice it, right? See here, 165 and 1080. Let us write here 165 and 1080. 1080 is greater than 165, so we'll consider it as A, and this we will consider it as B. So 1080 is equals to, we are doing using Euclidean algorithm till the remainder gets 0. Here we got the remainder as 0. So the last non-zero remainder is 15. So the GCD of what were the numbers? 615 and 1080, correct? GCD has become 15, which is the last non-zero remainder, 15. Now we got the GCD. So we are done with the first step. Now coming to the second step, 465 and 1080 should be expressed in the form of linear combination. How do we do that? We have already seen this step, correct? 1080 is equal to, sorry, let's take a pen. 1080 is equals to 1 into 615 plus 465. Let us take the same step here. 1080 is equals to 615 into 1 plus 465. From here, can we write 465? 1080 minus 1 into 615. We can write it in this format, correct? Now, we are also having the second one. From here, you can write 150. 150 is equals to 615 minus 1 into 465. True. Here in the place of 465 you can substitute this value, which is 615 minus 1 into 1080 minus 1 into 615. Now what does it become? There is a 615 term here, one more 615 term here. So what it becomes? 2 into 615 minus, there is only one term left, 1 into 1080. So we'll continue with it. Now we got it. We came till the second step, correct? Now consider the third step. 465 is equals to 3 into 150 plus 15. You can write 15 from here as 465 minus 3 into 150. Here, you know what is 150? We have just now we got it. 2 into 615 minus 1 into 1080. When you substitute in the place of 150, then if you solve it, you will get it as 1080 and 615 in terms of 1080 and 615. What was the linear combination? 615u plus 1080v. Is it true or not? You need to find u and v only, right? So here, how do we solve it? There is a term 3 into 2 of minus 3 into 2 of 165 minus 1 into 1080 is same as it is which is written. But 465, how do you write? Do you have already 465 here? So just substitute this value in place of 465 and now take common, that is 1080 and 3 times of 1080. That means what? 4. You got 3 plus 1 is 4, right? 4 into 1080. Now how many 615 terms are there? There is one 615 term and 3 2s are 6. 6 plus 1, 7 615 terms are there here. So you got it in this format, right? So here u is equal to minus 7 and v is equals to 4. Finally, you got the values of u and v, which is u is equal to minus 7 and v is equals to 4. So we have found u and v values by using linear combination and also Euclidean algorithm. So thank you so much for watching this video.